All right, let's dive deep today. We're going to be looking at some serious research, a paper all about using this thing called free energy to understand Log-Sobolev inequalities in mean field particle systems.
Yeah, it's a bit of a mouthful, I know.
Yeah, there are a lot of terms there. It sounds like we're in for some heavy lifting. We are. But we're not just going to be throwing jargon around. We're going to really unpack this research and see why it matters.
And we'll make sure that even the complicated parts, we'll make them clear. It's kind of like getting all the insights without having to spend weeks doing the math yourself.
Absolutely. We're not just skimming the surface. We're going deep. We'll be going page by page, even sentence by sentence when we need to. We're going to really define every term and follow the math, like step by step, so you can see exactly how the authors built their arguments.
And speaking of the authors, this is a full-blown research paper, chock full of equations and formal definitions. We're going to really take our time to explain the notation, all the derivation steps, the whole mathematical reasoning behind it. Yeah, so basically, if you're ready to understand how this research really works, well, you're in the right place.
Buckle up, because we're going deep. So our mission today is to figure out how this free energy thing can tell us about, well, about what happens in systems with a huge number of particles that are all interacting. The cool thing is, this criterion seems to work even when the system is near a critical point.
Yeah, those critical points, that's where things get really interesting, unpredictable. You know, like when water boils or freezes.
Exactly. Understanding those moments is often the key to understanding the whole system. So the paper itself, it's called A Criterion on the Free Energy for Log-Sobolev Inequalities in Mean Field Particle Systems.
Right. By Roland Bauerschmidt, Thierry Bodineau, and Benoit Dagallier.
And it's dated April 1st, 2025.
April Fool's Day.
Maybe a joke. I doubt it. Let's start with the abstract, like we always do.
Sure. The abstract basically gives you the main points of the paper. It says they found a criterion based on free energy, and if this criterion is met, it sets bounds on the Log-Sobolev constant for Langevin dynamics in mean field particle systems. A lot to unpack there.
Okay, yeah. Maybe we should start with mean field particle systems. Can we paint a picture of that?
So imagine you have a ton of particles, like a huge amount, like molecules in a gas or maybe agents in a financial model. In a mean field system, each particle, well, it doesn't interact directly with every other particle. Instead, we kind of simplify things. We approximate the effect of all the other particles on one single particle by just looking at the average influence of all the others.
So it's like instead of trying to track every single interaction, we just look at the big picture, the overall level of interaction.
Yeah, exactly. And this makes things way easier to handle mathematically, especially when you have, massive number of particles.
Okay, that makes sense. And what about Langevin dynamics? That was the other term. I think it describes how the system evolves over time, right?
Got it. Langevin dynamics is a way to model how particles move and change over time. It considers two main things: deterministic forces like gravity that kind of push the particles in a certain direction, and then you have random forces, fluctuations, like the random bumping around of molecules because of heat.
So it's like a combination of predictable forces and pure randomness.
Exactly. And mathematically, those random forces are usually modeled using something called Brownian motion. So Langevin dynamics basically shows us how a system moves towards a stable state, considering both the predictable and the random stuff.
Okay, got it. And what about the Log-Sobolev constant? The abstract said the free energy criterion puts some limits on it, so why is that a big deal?
Well, the Log-Sobolev constant is a number that basically tells you how quickly a probability distribution settles down into its equilibrium. So think about disturbing a system. You knock it off balance. The Log-Sobolev constant will tell you how quickly it goes back to normal.
So a bigger Log-Sobolev constant means it bounces back quicker.
Right, basically. And having uniform bounds on this constant means that the system's stability and the speed it reaches equilibrium, well, they don't get worse as the number of particles increases. And that's really important for these mean field systems where we're dealing with lots and lots of particles.
Gotcha. The abstract also mentions that this criterion works for, specific double well potentials with quadratic interaction. And this applies up to the critical temperature. And they also examine how the Log-Sobolev constant acts near this critical point. That sounds pretty important.
Yeah, it is. A potential basically describes the energy landscape of the system. A double well potential, well, imagine it like a landscape with two valleys. Those valleys represent stable states for the system.
Like two places where the system likes to hang out.
Exactly. And Quadratic interaction means the energy between particles depends on the square of their distance or some other property. It's a relatively simple kind of interaction, mathematically speaking. The critical temperature, as we mentioned before, is a specific temperature where the system's behavior changes drastically.
Like water turning into ice.
Right. So the fact that their criterion works even up to this critical point where things can get really sensitive is a big achievement. And by looking at how things change near this critical point, they're giving us a really detailed picture of how the system's stability changes during these transitions.
They then say it works for diluted mean field models on dense graphs, and it can be generalized to non-quadratic interactions using a mode decomposition.
Right. A diluted mean field model basically means that not all particles are interacting with each other directly. It's like a network where some connections are missing. A dense graph means there are still a lot of connections, just not all of them. So their criterion applying here suggests it's useful for more real-world situations where interactions aren't always so, uniform.
Makes sense. And non-quadratic interactions with mode decomposition?
Well, in the real world, interactions between particles are often much more complex than just simple quadratic forms.
Yeah.
The authors have figured out how to extend their analysis to handle these more intricate interactions using this mode decomposition technique. It's like breaking down a complex interaction into simpler pieces, kind of like different frequencies in a sound wave. Each mode captures a different aspect of the interaction.
So it's a way to simplify complex interactions into smaller, more manageable parts.
Yeah, exactly. They also mention that their method differs from the usual way this is done in physics, which uses scale decomposition. This scale decomposition works well for systems with interactions happening at different scales, like in condensed matter physics. But mean field systems, well, they don't really have those different scales the same way, so they need a different approach, and that's where their mode decomposition comes in.
Okay, that clears up the abstract. It seems like this paper is really pushing the boundaries of what we know about stability in these complex systems. All right, let's move on to section 1, the introduction. They get right to it, talking about understanding how the large time behavior of Langevin mean field dynamics works for a large number of particles.
They call this number dollars, and they give us equation 1.1.
Right, equation 1.1. This is the equation that tells us how the position of each individual particle changes over time. It's a stochastic differential equation. That means it includes both deterministic and random parts, just like we talked about with Langevin dynamics. All right, so let's break down this equation 1.1. It says H is like d, dt im, d type 1, dt x by t to t, plus squart is dt chi. So on the left side, we have dxit. I think that represents how the position of the Ike particle changes over a really tiny time interval, right?
Yeah, exactly. It's the infinitesimal change in the particle's position.
And on the right side, we have, well, a bunch of terms. First, we have nabla, vit, dt. So what's baller here? And what does that upside down triangle thing, the nabla, mean?
Well, Vela is the confinement potential. Think of it as an energy landscape that tries to keep the particles within a specific region. Like it could be a valley, and the particles want to stay at the bottom.
And the nabla.
Nabla is called the gradient. It basically tells you the direction and rate of the steepest increase of a function. So a nabla v represents a force on the particle at its current position, trying to push it towards where the potential energy is lower.
So it pushes the particle down the valley towards the bottom.
Right. Exactly. The dt all just means it's the change over a tiny time interval.
Okay, that's one force. Then we have frap P1NT, sum J1N, WXIT. This one looks a bit more complicated. What's dollars and what's nabla dollars doing here?
Okay, so dollars is the symmetric interaction potential. It describes the potential energy between pairs of particles.
So how much energy there is depending on where the two particles are relative to each other.
Yeah, exactly. The symmetry just means the energy is the same no matter which particle you call first and which one you call second. Now, nabla 1 WXIT, XJT, well, that's the gradient again. But this time, it's the gradient of the interaction potential, but only with respect to the position of the Ascart particle.
So it's like the force on the ith particle due to its interaction with the jth particle?
You got it. And the big sigma, the sum J1, means we add up the forces from all the other particles in the system. The Furquan suggests we're looking at the average interaction, which is typical in mean field models. And dollars, remember, is the temperature, which kind of scales the strength of this interaction.
Okay, so it's the total average force from all the other particles. And finally, we have plus square bio. Now, this one has that d-Boyer thing. What's that all about?
So, Boyer represents independent standard Brownian motions. Remember, Brownian motion is that random movement we talked about, like dust particles jiggling around in the air. T-biot is just a tiny change in this random motion at a specific time. The squirty in front scales the random fluctuations with the temperature. Basically, higher temperature means more jiggling around.
So this last term is all about the random thermal noise in the system.
Got it. So equation 1.1 really captures those three things we talked about. The force keeping the particle in a region, the average force from all the other particles it's interacting with, and the random jiggling due to heat. Yeah, precisely. And then the authors point out that when $9, the number of particles, becomes super large, this system's behavior starts to look like something called the Minkowski-Vlasov equation. This equation describes how the probability distribution of just one particle evolves in this mean field created by all the other particles. But they make it clear that we're going to focus on the original system with a finite number of particles.
Right. So we're sticking with the interacting particles and not diving into the Minkowski-Vlasov equation. They also mention a whole bunch of other research that's been done on this topic, but they're only going to talk about the stuff that's directly relevant to their work, which is good because there's a lot out there. Okay, the next big thing is the invariant measure, which they denote as MNNTDXU in equation 1.2.
Right. The invariant measure is a probability distribution that tells you about the likelihood of finding the system in specific configuration. And it's called invariant because, well, if you start the system with this distribution, it stays in that distribution forever as it evolves. It's the stable equilibrium state of the system.
So it's like once the system reaches this state, it just kind of hangs out there.
Yeah, pretty much. Okay, so equation 1.2 says MNT, Beck1 semi dn, WXI, XT day, WXI, XJ. Now, what's ZNT day?
ZNT, that's just a normalization factor. It's a constant that makes sure that the whole thing is a proper probability distribution, so that all the probabilities add up to 1.
Right. Without it, we just have something proportional to a probability.
Okay, and then we have that big exponential term, XP pre 1 Siam A, Gry 1 N, WX, XJ. What's that all about?
That term accounts for the interactions between all the particles. The sum is basically the total interaction energy of the system. The negative sign means that lower energy configurations, meaning more stable ones, are more probable. And the factors of Frat1T and Frey are there for scaling purposes, like we saw in the Langevin equation.
Gotcha. So lower energy means more likely. And lastly, we have the product, Padley 1N. What's alpha V ds?
Alpha V dx is defined right after that. It's basically the probability distribution of a single particle if it were only affected by the confinement potential dollars. The product just means we're looking at non-dollar independent particles, each with that same individual distribution. So the full measure, non-NT, combines the individual particle stuff with the effects of their interactions.
So non-NT is like a snapshot of the whole system, taking into account both the individual particles and their interactions with each other, all at equilibrium.
Exactly. And the authors end the page by saying that throughout the paper, they're assuming that non-NT is a proper probability measure. That means that ZLN-NT is finite, which basically means that the potentials $1 have to be well-behaved enough for everything to make sense mathematically.
Okay, so we made it through page 1. We've got our basic player set up. Now on to page 2, where they bring in this idea of free energy. That's a big one in statistical mechanics.
Right. Free energy basically combines the system's internal energy with its entropy. It's super important for figuring out the equilibrium state at a specific temperature. Here, they define 50 Friller for a single probability measure, fractions. This represents the free energy per particle in the large dollar limit, like when you have a huge number of particles.
Okay, and equation 1.5 gives us the definition. FP50 fav gx plus fraf bx wineway mer x. It's got 3 terms.
The first one, Rodway x me x re, that looks like an entropy term.
It is. It measures how spread out the probability distribution through L is. More spread out means higher entropy.
The second one, ux rho dx, that's the average value of the confinement potential Vx Vx ray when 6 Kazera is distributed according to Dray. So it's like the average energy due to the confinement.
Right, exactly.
And the third term, FBX way, this one has to be the contribution from the interaction potential dollars, right? Yeah. We're looking at pairs of positions, 6 terms, weighted by the probabilities, and there's that Franke factor again. This term represents the average interaction energy between pairs of particles, assuming they're distributed according to Archon.
So it's all about how the particles interact with each other on average. They also say that arc goes up to infinity if Archon is in a nice smooth probability distribution. That makes sense, because some of these terms would become, meaningless if Morcall was too weird.
Right, like if it was concentrated at a single point.
Okay, next they say that under some general conditions, this free energy $5 saw has at least one minimizer, which I guess means a probability distribution that gives the lowest possible free energy. They even cite a reference for this 40.
Yeah. These minimizers of the free energy, they correspond to the equilibrium states of the system in the large not-all limit. So finding them is super important in statistical mechanics.
Then they say for high enough temperatures, $50 has only one unique minimizer. But for low temperatures, there can be multiple minimizers. That sounds a lot like what we were talking about with phase transitions.
It is. At high temperatures, things are more random, so you tend to have just one stable state. But at lower temperatures, the energy from interactions becomes more important, and the system can settle into different stable configurations, meaning multiple minimizers for the free energy.
And this leads us to the critical temperature $T$ in equation 1.6. They define it as the lowest temperature above which $50 always has a unique minimizer. It's the boundary between having one equilibrium state and having multiple states.
Right. T-T-L marks the point where phase transitions start to happen.
And the authors say their main goal is to relate this critical temperature to how the actual Noller particle dynamics from equation 1.1 relax towards equilibrium.
Yeah, they want to connect the static idea of free energy in equilibrium states with the dynamic idea of how the system evolves over time.
And they're going to do this using the Log-Sobolev inequality that we talked about earlier. They define it in equation 1.7 for the mean field measure, men and NTF, NNT, MNT, 10x2, NNT, NNT, and MNT. This is supposed to be true for any smooth function dollars that depends on the positions of all Noether uppercles. So what's ENNTF?
Okay. NNTF is the entropy of the function $5 with respect to the probability measure. Entropy measures how spread out or concentrated the values of 50 are under the distribution N and T. If $5 is pretty much constant, its entropy is close to zero. But if it takes on a wide range of values, its entropy is higher.
Gotcha. And what about that Nobel scored on the other side of the inequality?
That's the gradient again, but this time it's the gradient of the square root of the function $5. It basically measures how quickly the function $5 is changing with respect to the particle positions. If $5 is smooth and doesn't vary much, this gradient is small.
Okay, so this Log-Sobolev inequality relates the spread or variability of $5 to how smooth it is with a constant gamma that determines how strong the connection is.
Exactly. And a measure that satisfies a Log-Sobolev inequality with a large gamma is really well behaved. The dynamics associated with that measure will converge to the equilibrium distribution exponentially fast, and gamma controls the speed of that convergence.
They mentioned that if $5 aren't too wild, there's an optimal constant gamma NLS for which this inequality holds, and they reference a book 32 for more background on this Log-Sobolev stuff. Now, the big goal of this paper is to get estimates for this constant gamma NLS that don't get worse as the number of particles increases. Why is that so important?
Well, if gamma NLS depends on $none and it decreases as $none grows, that means larger systems take longer to reach equilibrium, which would be a problem. Having a uniform bound means that the system's stability and the speed of convergence are kind of guaranteed no matter how many particles you have.
So it's about making sure the system doesn't become unstable or sluggish as it gets bigger.
Exactly. And they want to do all of this using only the mean field free energy of $50. So they're looking for a way to predict the dynamic behavior of the system just from its static properties.
Okay, so they've set up the whole problem. We've got our model, the equilibrium measure, the free energy, the critical temperature, and the all-important Log-Sobolev inequality. Now let's turn to page 3, where they start talking about how this uniform bound on the Log-Sobolev constant is related to phase transitions.
Right. They start by acknowledging that finding these uniform bounds has been a really hot topic in research for a long time. And they remind us that those phase transitions we talked about are fundamentally determined by the free energy $50.
They mentioned that if the interaction term in the free energy, that cool mapsto into a cull thing, if it's not convex, then you can get phase transitions depending on the temperature. And in those cases, the Log-Sobolev constant might vanish as the number of particles increases. What does it mean for the constant to vanish?
Well, it means that as the system size grows, the Log-Sobolev inequality becomes less and less useful. Remember, a larger constant means faster convergence to equilibrium. If it goes to zero, the system can become extremely slow to settle down. This often happens when you have multiple stable or metastable states, where the system can get stuck for a long time before finding the true equilibrium.
So it's like the system gets indecisive and takes forever to make up its mind.
Yeah, kind of. And they say that even without a true phase transition, if the free energy $50 has multiple local minima, the system can get trapped in those local minima. and the Log-Sobolev constant can still vanish. So just having a unique minimizer isn't enough. The shape of the free energy landscape is also important.
Okay, that makes sense. Then they say that for really high temperatures or weak interactions, we don't expect to see phase transitions or these metastable states. In those cases, you should have a uniform bound on the Log-Sobolev constant, which apparently has been shown in another paper 31.
Right. High temperatures essentially smooth out the energy landscape, so there's less chance of the system getting stuck in a local minimum. The thermal fluctuations are strong enough to kick it out of those traps.
Makes sense. And then they mentioned some recent research on a specific type of interaction called flat convex interactions, referencing papers 4722, and how this has been extended beyond that case 41. It seems like this whole area is still very active.
Absolutely. Figuring out the conditions for the Log-Sobolev inequality to hold is still a big challenge, especially for complex interactions.
All right. They then restate their goal, which is to figure out how the behavior of the Log-Sobolev constant is related to the free energy, depending on the potentials 5 on $, and the temperature $. And they tell us their approach is based on something called renormalization ideas.
Renormalization is a set of techniques that were originally developed in physics for dealing with systems at different scales. The basic idea is to focus on the effective degrees of freedom at the scale you're interested in and kind of average over everything else. In mean field systems, you don't really have spatial scales, but the idea is similar. You try to simplify the system by introducing some auxiliary variables and then study the behavior of those new variables.
So it's like zooming out to get a simpler picture of the system.
Exactly. They mentioned that this method has been used before for similar problems, 14, 10, and they're extending it to continuous models on random graphs.
Random graphs, like those networks we were talking about earlier.
Yeah, random graphs are networks where the connections between nodes are random. They're good models for lots of real-world networks.
Okay, so they're taking this method and applying it to a more general setting. For quadratic interactions, their approach can analyze the Log-Sobolev inequality all the way up to the critical temperature. They mentioned two theorems, 1.3 and 1.5, for different types of graphs, and their method uses a special decomposition of the interaction matrix, which basically reduces the complex dynamics of the whole system to a single slow mode that controls the big picture behavior.
Right, the spectral decomposition. It's like finding the main frequencies that dominate the system's behavior, especially near criticality.
They also mention other methods that have been used, but their approach seems particularly well suited for these mean field systems. Now, turning to page 4, they start talking about non-quadratic interactions, which are more challenging, right?
Yeah, non-quadratic interactions are harder to analyze because you can't just use those simple spectral decomposition techniques. So they mainly focus on fully connected graphs for this part.
And they remind us that for flat convex interactions, where the free energy is nice and convex, there's no phase transition. And they cite some papers where the Log-Sobolev inequality has been proven in those cases, 4722.
Right. Convexity is usually a good sign that things are going to be well-behaved mathematically.
But they're interested in cases where the interaction is more complex and might lead to phase transitions. So they introduce a specific type of non-convex interaction where they can still use a kind of mode decomposition, similar to what they did for the quadratic case. And by doing this, they can get a criterion that only depends on the free energy and can tell us whether the Log-Sobolev inequality holds. This is a key part of extending their approach to more realistic systems.
Exactly. They're finding a way to break down those complex interactions into simpler pieces, even when they're not quadratic.
And they make a connection to work that's been done on other types of systems, like those with short-range interactions, citing some papers 8, 9, 13, 12, 11. But they point out that mean field systems are different because they don't have those different length scales, so their mode decomposition approach is more appropriate.
Right. It's all about adapting the methods to the specific structure of the problem.
Okay, finally, they introduce assumption 1.1 on the confinement potential of Wöhlers. It says that $5 can be split into two parts. Vim tel v, where Weiber is what they call uniformly convex, and tel v is either Lipschitz continuous or bounded. What does all that mean?
Basically, it means Weiber is well behaved. The uniformly convex part means that virus has a strong confining effect, kind of like a steep valley. And the condition on tel v ensures that it doesn't mess up this nice confining behavior too much.
Got it. So it's all about making sure the particles stay where they're supposed to and that the math works out nicely. Now, on page 5, they jump into the simplest case, quadratic interactions, where Hortelak's y equals x, y grew. They say this leads to a single mode and scale, and the continuous Curie-Weiss model is an example.
Yeah, the Curie-Weiss model is a classic example in statistical mechanics. It describes how particles interact with each other based on their average magnetization. The authors say they're generalizing previous results for this model by looking specifically at the mean field free energy.
And they define something called the coarse-grained free energy. In equation 1.8, it's the minimum value of the regular free energy foreign dollar over all probability distributions that have a certain mean, which they call xi. What's this coarse graining all about?
It's basically a way to look at the system at a larger scale. Instead of looking at the detailed distribution drill, they focus on just the average position dollar of the particles. It's like zooming out and blurring the details to see the bigger picture.
Okay, so we're simplifying the system by focusing on averages. They then say they want to relate the Log-Sobolev inequality for the original null particle measure to properties of this coarse-grained free energy, which describes the large-scale behavior. They focus on temperatures above the critical temperature, and they assume that something called the gradient flow of head of t, given by equation 1.9, relaxes exponentially fast to the minimum of head of t.
Right. The gradient flow is basically a way to describe how a system evolves according to the forces defined by the free energy. Exponential relaxation means that it approaches the equilibrium state very quickly.
So it quickly settles down into the most stable configuration. And they mention that this is the same as head of t satisfying the Polyakov-Givitz inequality, or PL inequality for short, in equation 1.10. This PL inequality seems to be a way to guarantee that the system will relax to equilibrium efficiently.
Exactly. The PL inequality basically prevents the free energy landscape from having flat regions where the system could get stuck. It ensures a certain steepness that helps the system roll down towards the minimum.
Okay, that makes sense. Then they present lemma 1.2, which is from another paper 23, and it seems to be a crucial connection between this macroscopic PL inequality and a microscopic Log-Sobolev inequality.
Yeah, lemma 1.2 is important because it connects a property of the coarse-grained free energy, which is a large-scale thing, to a property of a related probability measure, which is a microscopic thing.
Yeah.
It basically says that if the coarse-grained free energy satisfies the PL inequality, then this other measure will satisfy a Log-Sobolev inequality, and its constant will scale with no dollar the number of particles.
So it's linking the large-scale behavior to the small-scale behavior.
Exactly.
And this brings us to theorem 1.3, the big result for quadratic interactions. It says that if the confinement potential dollars is well behaved and the interaction is quadratic, and if, for temperatures above the critical temperature, the coarse-grained free energy satisfies the PL inequality, then the original null particle measure will also satisfy a Log-Sobolev inequality, and its constant won't depend on non-dollar.
That's it. Theorem 1.3 is a really big deal because it connects a condition on the large-scale free energy to a property of the microscopic system. And the connection doesn't get worse as the system grows. It's a way to guarantee stability and good behavior at the microscopic level, just from looking at the big picture.
Okay, that's pretty amazing. Then comes corollary 1.4, which looks at a specific type of confinement potential called a double well potential. They focus on one dimension and consider a specific form for the potential, that phi vxx, frac I4, lambda frac I2 thing, or more generally, any potential that belongs to a class they call GHS potentials, which we'll see later. The corollary says that for temperatures above the critical temperature, the null particle measure satisfies a Log-Sobolev inequality with a constant independent of dollars. And it tells us how a Log-Sobolev constant behaves near the critical temperature, that it vanishes linearly as the temperature approaches the critical temperature.
Right. Corollary 1.4.
Ever get that feel like you're drowning in information?
Yeah.
You know, the more you read, the less you feel like you actually know.
Yeah, definitely. It's like you're trying to put together a puzzle, but the pieces just keep multiplying.
Exactly. Well, that's where we come in. Welcome to the deep dive.
We sift through all those research papers, the articles, all the dense stuff. We find the real gems, the insights that make it all make sense.
We break it down for you, make it clear, sort of like intellectual Sherpas, you know, guiding you through all the complexity.
That's a good analogy. And today's journey, it's a fascinating one. We're diving into a research paper.
You provided this one, actually. It's called A Criterion on the Free Energy for Log-Sobolev Inequalities in Mean Field Particle Systems. Catchy, right?
Well, it's definitely a mouthful.
Yeah.
Might sound a bit intimidating, I'll admit.
Yeah, maybe a little bit.
Yeah.
So let's unpack it a bit, shall we? First off, mean field particle systems. What are we talking about here?
Okay, so imagine this. You have a ton of tiny things. It could be atoms, people, even neurons in a brain.
Right.
In a mean field model, we're basically simplifying things. We're saying each of these things, they're not interacting with every other thing in some super complicated way. Instead, they feel an average influence.
Right.
We call that the mean field.
Okay, I get it. So it's kind of like if you're in a huge crowd, you're not listening to every single person talking.
Right, exactly. You get the overall buzz, the energy of the crowd, but not all the individual details. And these models, they're surprisingly useful. They help us understand how big systems behave in all sorts of fields.
So big picture stuff, focusing on the average, not getting lost in the weeds. Makes sense. Now, the title also mentions Log-Sobolev inequalities, another one of those terms that might make your eyes glaze over, right?
It is a bit technical, but think of it this way. It's all about how fast a system settles down, reaches a stable state. Like imagine you drop a rock in a pond. How long does it take for the ripples to die down?
Okay, I can picture that.
The Log-Sobolev inequality, we often call it LSI, gives us a way to measure that settling down time. Mathematically speaking, of course.
Right, right.
And this paper, it's all about finding the right conditions connected to the system's free energy that guarantee those fast settling times.
Gotcha. So connecting this idea of free energy, something we kind of get from thermodynamics, to this more abstract, how quickly things settle down, math. And the map for our journey today, this research paper full of equations, definitions, all that good stuff. And you specifically asked us to dive deep into that, right? The math, the proofs, the whole shebang.
That's right.
So our mission is this, to figure out how free energy and this Log-Sobolev thing are linked, and what that tells us about how these systems behave, especially when they're near some kind of tipping point. We're going deep, buckle up.
So first things first, got to lay some groundwork. The paper looks at these Langevin mean field dynamics, lots of particles in some space. Their equation, 1.1, sets it all up. What jumps out at you when you see that?
Well, on the left side, there's 20 Cias. That I probably means we're talking about a specific particle, right?
Exactly. Particle number I. And the T, that's time, of course.
Yeah. So it's about how that particle's position changes over time. Then, on the right side, we have a bunch of terms added together. The first one inside the brackets is nabla vs. Now, nabla usually means a gradient, doesn't it?
It does. The gradient, it points in the direction where the function increases the fastest. Think of it like if you're climbing a hill, the gradient tells you the steepest path up.
Huh, okay.
So here, it's like a force acting on particle I. This force comes from some potential dollars.
Gravity pulling things down a slope?
Yeah, something like that.
Okay.
So symmectal I is the position of particle I at time t.
In some multidimensional space, right?
Right. That's the driller part. The belly is the number of dimensions. Could be 1, 2, 3, whatever. And VLA is what we call the confinement potential. It's a smooth function. And it's the same no matter how you approach a point. Symmetric, they call it. It takes a point in that space and gives you a number.
Yeah.
The potential energy at that point.
Okay. So if beta describes like a valley, the gradient would point uphill and the force would pull the particle down, right?
Right, towards lower potential energy. And then we have this other term inside the brackets, sum J1 and nabla 1 W exit. This one looks more complicated.
Yeah, there's a sum in there. It looks like it's going over all the other particles, like how particle I is influenced by all the others.
Precisely. Wx my A is what we call the interaction potential. Again, it's symmetric and smooth.
Meaning how particle I affects J is the same as how J affects I.
Exactly. The nabla W dollar part, that's saying we're taking the gradient of dollars, but only with respect to the first position, the X, the position of our particle I. And the whole thing is scaled by $1 NDT, and being the total number of particles over the temperature.
Okay, so this is where the mean field part really comes in, right? We're averaging the interaction over all the other particles.
Exactly. Paul dollars gives us that average. And the temperature, T, it's scaling how strong that average interaction is. The whole term in those brackets. That's the total force acting on particle I at that moment in time. It comes from both the external potential, the landscape, and the average interaction with all the other particles.
So it's being pushed and pulled by the environment and by its neighbors in a way. Then we have that last term in the equation, plus squirt d-bit. That d-bit looks random.
It is. It represents random fluctuations. The I means it's specific to each particle. And that T under the square root, yep, temperature again.
So hotter means more randomness, more jiggling around.
Exactly. Partum is a mathematical way to model that jiggling. Like imagine tiny particles bouncing around in a fluid. that random motion. And it's independent for each particle. That's important. So the whole equation, 1.1, it's telling us how each particle's position changes over time. It's got that deterministic force from the potentials, but also this random temperature-dependent jostling. This is our Langevin mean field dynamics in action.
Okay, I think I'm getting the picture. Particles wandering around, influenced by this landscape, their neighbors, and some random kicks. Now, what happens to this system over a long time? Does it settle down?
Yeah, it does.
Yeah.
Well, under the right conditions, that is. The potentials, V and W, need to be well-behaved. Confining enough, you know.
So if things are like pushing them together enough, they'll eventually settle down.
Exactly. And when it does, we describe that state with what's called an invariant measure. That's MNT dx over an equation, 1.2. It's basically a probability distribution. It tells you the chances of finding the system in any particular arrangement of those particles once it's reached equilibrium.
I see. And looking at that equation, MNT dx is proportional to a bunch of stuff multiplied together. There's a ZNT at the bottom. Looks like some kind of normalization factor.
Right. ZNT is just making sure that M&AT is a proper probability measure. Meaning, if you add up the probabilities of all possible arrangements, you get 1. It's called the partition function sometimes.
Okay, makes sense. Then in the top part, there's this exponential term, xp fractio 1tn semi j1n wxi xj1. Looks like it involves the interaction potential that, like, how likely a configuration is depends on how much those particles interact.
Exactly. It's accounting for the energy of those interactions. The sum there, it's going over all pairs of particles, including when I equals j. And the factor out front, that's all PTNE, it's scaling that energy.
Right. And then we have this other part, Prodi 1 and alpha v. This is a product over all the particles. And it involves alpha v dxa, which is defined in equation 1.3 as proportional to E Vx. So this looks like it's saying if the particles were all independent and only felt the external potential dollars, this is how they'd be distributed at equilibrium.
You got it. Each particle on its own, just feeling the landscape, no interactions.
So the interaction term in equation 1.2 is like it's adjusting that independent distribution. It's factoring in the fact that, hey, these particles actually do interact with each other. And that assumption about ZNT always being finite for $2, that just means there's always a well-defined equilibrium at any positive temperature.
Right. Now, when you have a huge number of particles, a really big N, things simplify a bit. We can use what's called the free energy to describe the system. That's VIT of TA in equation 1.5. George represents the probability density for a single particle, but in this macroscopic limit where N is huge.
Okay. And looking at equation 1.5, I see 3 terms there. First one, dx yo. This reminds me of information theory. Isn't this like the entropy of the distribution?
It is. It tells you about the spread, the disorder of that distribution. A uniform distribution where everything's equally likely has the highest entropy.
The second term is nmtxc. So since dx is about how a single particle is distributed in this large n limit, and venxc is the potential energy, this term must be about the average potential energy of a particle, right? Average over all the possible positions according to the Roby.
Right on. The expected value of the potential energy.
And the last term, NE2 at E2, NAX. We're integrating over pairs of positions now. This is going to be about the interaction energy, right? Between two particles, assuming they're both distributed according to...
Exactly. We're in the mean field limit, so we're assuming the particles are kind of independent of each other.
Yep.
So this is the average interaction energy scaled by 1t day. The half is there, so we don't count each interaction twice.
Right, right. So the free energy, this FET of T, it's like a balancing act. It wants high entropy, lots of spread, but also low energy.
Exactly. The system will try to find that sweet spot, the distribution, that minimizes the free energy. And the authors say that usually there's at least one such minimum, at least one state where things are balanced.
Now, equation 1.6 introduces T to the law, the critical temperature. Sounds important, like something might change drastically around this temperature.
It is important. T-tail lauder is the lowest temperature where, if you're above it, the free energy only has one global minimum.
So above T-tailer, only one state is the most stable, the most balanced. But below it,
you could have multiple minima, multiple states that are all pretty stable. That's where things get interesting. That's a phase transition.
Like water turning to ice.
Exactly. Or a magnet losing its magnetism when it gets too hot. Big changes in behavior. Now, the paper's big focus is to connect this critical temperature to how quickly the system settles down. Remember, that's where the Log-Sobolev inequality comes in.
Right, the LSI. Equation 1.7 gives us the formal definition, lots of symbols in there, but it's for the measure mn/nt with a constant gamma dollars. It involves a function, $5. It takes configurations of those n particles and gives you a non-negative number. And it's got to be 0 outside some bounded region, compactly supported, they call it.
Yep. And mntf is the entropy of that function, but with respect to that probability measure. It measures how much dollar fluctuates, how non-uniform it is according to that measure.
Okay. And on the other side of the inequality, we've got gamma EN/NT 10 to F2. So we're taking the gradient of the square root of full dollars. That's with respect to the positions of all those particles. Then squaring it and integrating it with respect to the measure. And gammaless is the Log-Sobolev constant.
Right. So basically, if $5 has high entropy, meaning it varies a lot according to the equilibrium distribution, then its gradient, how much it changes as you move those particles around, has to be large on average.
The bigger gamma is, the stronger that connection is. And I guess a larger gamma means things settle down faster, right?
Exactly.
Yeah.
Gamma NLST is the best possible, the largest Log-Sobolev constant you can get for that measure at that temperature. The authors say that usually this inequality holds with some positive gamma NLS, at least under mild conditions on those potentials.
So the big question is, what happens to this gamma NLST? How does it depend on the number of particles? How is it linked to the free energy? And especially what happens as you get close to that critical temperature?
Exactly. And ideally, we want to find some kind of lower limit for gamma NLT that doesn't depend on the number of particles, because that would mean even if you have a huge system, it'll still settle down nicely.
Makes sense. So we've got the dynamics, the equilibrium, the free energy, this critical point, and the LSI. Lots of pieces. Now, the paper starts looking at specific scenarios, starting with quadratic interactions, the simplest case, I guess.
Yeah, starting simple. In section 1.1, they look at dollars, xy, met as y, cax y, xx, equation, one middle lane. That 6xy thing, that's the inner product or dot product, like multiplying the components of those vectors and adding them up. This kind of interaction leads to what they call single mode system, and they define a one-mode, coarse-grained free energy ham in equation 1.8. And being a vector in that same space, what's the idea behind this coarse graining?
So we're simplifying things even more.
Exactly. We're zooming out, looking at the big picture. The FFT of the minimum value of the full free energy, but only for distributions, draw, that have a specific average position. That's what mine represents.
So instead of worrying about where each individual particle is, we're just looking at the average position of the whole bunch, like their center of mass.
Perfect analogy. We're coarse graining, focusing on that key collective variable. And then in equation 1.9, they talk about the gradient flow associated with this coarse-grained free energy. It's nabla habla. That dot on top of nabla habla, that's the time derivative, right?
Yeah, how the average position changes over time.
Right. And it's equal to minus the gradient of the coarse-grained free energy. So the average position, it moves in the direction that makes the free energy decrease the fastest. Systems like to go downhill towards lower energy.
Makes sense. So if you start with some average position, it'll evolve over time, following that gradient flow until it reaches a minimum of the free energy, a stable point. And they say if tiro time are as dollars, meaning we're above that critical temperature, and there's only one global minimum, then this gradient flow will lead to that minimum as time goes to infinity.
Exactly. It relaxes to that most stable state. And they connect this to what's called the Polyak-Jurchasiewicz inequality, or PL inequality for short. That's in equation 1.10. It's Polyak-Jurchasiewicz being that global minimum. What does this tell us about the free energy landscape?
So on the left side, we have the difference between the free energy at some point M and the free energy at the minimum, like how much higher we are than the bottom of the valley. And on the right, it's the squared magnitude of the gradient. So it's saying the steeper the slope, the further we are from the bottom.
In essence, yes. Gamma PL is the key player here. It controls how steep those slopes are. The bigger gamma PL is, the steeper the free energy landscape. No flat areas where you can get stuck.
So this PL inequality, it's saying the free energy landscape is well behaved in a way. And they connect this to the LSI in lemma 1.2. It says if FMTM satisfies this PL inequality, then a related probability distribution, the one that's proportional to EM and T, it satisfies the LSI.
And the constant in that LSI, it scales with the number of particles. That n into our term just means something that goes to 0 as n gets huge.
So we're connecting the macroscopic, that free energy landscape, to the microscopic, the LSI. And theorem 1.3 takes it even further. It connects it back to the LSI for the original measure, the one for all those M particles,
Yep.
MNTM.
Right, so if that confinement potential, $5, is well behaved. That's assumption 1.1, and we have this quadratic interaction. And if our free energy satisfies the PL inequality above that critical temperature, then MnT2 satisfies the LSI. And the constant in that LSI, it doesn't depend on n.
That's huge. Even for a system with tons of particles, it'll still settle down nicely because of this property of the free energy. And in corollary 1.4, they look at a specific kind of potential. Double well potentials, kind of like two valleys next to each other.
Yeah, like a potential with two stable states. It applies if $5 belongs to this GHS class, which has some technical conditions. And they show that for these potentials, the LSI holds above TLSI with a constant independent of n. And as you approach TLSI from above, the LSI constant decreases linearly with the temperature difference.
So as you get closer to that critical point, the settling down gets slower and slower, but in a very specific way.
Right. And they mention in 1.14 that a similar result holds for a slightly different interaction potential, frat rho xy for 1,2,2. It's essentially the same physics, just with a different way of writing the interaction. Okay, so that's the story for quadratic interactions when everything's connected to everything. But in real life, that's often not the case. So in section 1.2, they look at non-complete graphs, more realistic interactions, where not every particle directly interacts with every other particle.
More like a network, then.
Exactly, like a social network or neurons in a brain. Not everything's connected to everything else. So they introduce a graph, GNE dollar, to describe this. It has n vertices representing the particles and edges between them representing the interactions. They use an adjacency matrix, A, to keep track of who's connected to whom, and the interaction potential is modified. It becomes 1dNES for 1dN, T G, 1N, AX, JX, GAJ. D dollars being the average number of connections each particle has.
So the sum isn't over all pairs anymore. It's only over those connected by an edge in the graph. Okay, and then they have assumption 3.1, which puts some conditions on this graph, right? Something about spectral properties.
Right. It's about how well mixed the graph is, in a way.
Mm-hmm.
It involves the eigenvalues of that adjacency matrix. It's saying that even though the graph might be random, if the average degree is high enough and the eigenvalues are kind of concentrated around 0, except for one special one, then it behaves nicely.
Yeah.
Lemma 3.2 says that random regular graphs and Erdos-Renyi graphs, if they have large enough degrees, they usually satisfy this assumption.
So even with random connections, if they're well connected enough, things still work out. Then in section 3.2, they talk about decomposing the measure again. But it's a bit more complicated now, right?
Yeah, because of that graph structure. Instead of a single auxiliary field, we now have matrix B phi, which is based on that adjacency matrix. The renormalized potential also changes. It becomes VTB phi. And the conditional measure, the one for fixed phi, it's not just a product of independent things anymore. The particles are still coupled through that graph structure.
So it's not as simple as before. And theorem 3.4 gives a bound on that Log-Sobolev constant, gamma G and LS, for temperatures above TLRPAN. What does it say?
It basically says if you have a large enough system and your graph satisfies that assumption 3.1 and the potential is of that double well kind, then the LSI still holds with a constant that doesn't depend on the number of particles. It's a bit messy, but the key is that the LSI is still well behaved above TTB psi, even with this graph structure.
Okay, good to know. And they get this by using a couple of propositions, 3.5 and 3.6. What are those about?
Proposition 3.5 shows that even with that graph structure, the conditional measure, the one for a fixed B and a FA, it still satisfies an LSI. The constant depends on the graph, but it's still well defined. They use some fancy math to prove this, involving further decompositions and a thing called the Becquerel-Emery criterion, which is a powerful tool for proving LSIs. And proposition 3.6, it compares the renormalized potential for the graph case, VTB, to the one we had before, the fully connected case.
Right. So how different are things when you add that graph structure?
That's what proposition 3.6 is getting at. It says that if the original renormalized potential is convex enough, which it usually is above TTDC for those double well potentials, then the graph 1 is also convex. And the difference between them is small, controlled by that epsilon left from assumption 3.1.
So the graph doesn't mess things up too badly as long as it's well connected enough. Okay, and what about below T, Thomas? I remember they had something about that in theorem 1.5. Something about the LSI constant going to 0.
Yeah, section 3.6 tackles that. They show that below TTCT, the LSI constant for the graph case, it does tend to 0 as the system gets bigger. But it's a bit tricky to prove. They use something called the Poincare inequality, which is a bit weaker than the LSI, but still useful. And by constructing a specific test function, they can show that this Poincare constant gets really, really small. Exponentially small, in fact, which implies the LSI constant also gets tiny.
So below $7 billion, things really slow down. Makes sense, since there are multiple stable states now, the system can get stuck in one of them for a long time.
Exactly. Okay, ready for the grand finale, section 4. This is where they go all out looking at general interactions, not just those nice quadratic ones. This is where the math gets hardcore.
Bring it on. I think I'm starting to get used to all of this. So they start with assumption 1.7 again. That's the one about decomposing the general interaction, Wn, into a nice part, plus dollars, and a more complicated part, $1.
Right. And dollars has that quadratic term we've been dealing with, but also this extra stuff. They represent it using a mode decomposition. It's like writing it as a sum of simpler functions with some coefficients. And they have all these conditions on those functions and coefficients.
To make sure things don't blow up, I guess. Then they define these Hilbert spaces, HE to learn and color, related to those modes. And they introduce the multimode renormalized potential, VT psi, in definition 4.1. It looks similar to the ones we had before, but it involves these modes now. And they have a definition for strong convexity again in equation 1.25. Something about the second derivatives of being positive definite.
Yeah, it's about the curvature of the free energy landscape again. But now it's in this multidimensional space of those mode averages.
Okay, more dimensions, more fun. And their main result, theorem 1.8, it says that if this multimode renormalized potential is strongly convex, then you have a uniform LSI for the original measure, even with these crazy general interactions.
Yep, that's the big one. And in remark 1.9, they point out that the quadratic case we did before is just a special case of this. The mode decomposition is simpler then, only involving a few modes related to the position.
Ah, so it all fits together nicely. And in remarks 1.10 and 1.11, they mention some famous models from statistical mechanics, like magnets and spins. They say their approach can be used to understand those too. Pretty cool. And then in section 1.4, they talk about possible generalizations. Even more complicated scenarios like unbounded spaces and infinitely many modes. Lots of open questions still.
Always is in research. Okay, so that's the big picture. The paper sets up this framework for connecting the free energy to the LSI for all sorts of interactions. But you wanted to see the proofs too, right? The nitty-gritty details.
Absolutely. Let's get into the weeds. Section 2 is where they prove the results for those simple quadratic interactions. They start by introducing this renormalized potential, VTPI, in equation 2.5. They get it using this Hubbard-Stratanovich identity equation 2.1. What's going on there?
So remember how in the quadratic case we had all those pairs of particles interacting? That sum over I and j.
Yeah.
Well, the Hubbard-Stratanovich identity, it's a trick to get rid of those pairwise interactions. It introduces a new variable, this auxiliary field.
Yeah.
And instead of particles interacting with each other directly, they now interact with this field, which is randomly distributed.
So it's like instead of a complicated dance between all the particles, we have each particle doing its own thing, but influenced by this common environment, this VTO.
Exactly. Much simpler to analyze. And that VT phi, it tells you about the distribution of this field, how likely different values are.
Okay, I see. So we've simplified things. And in equations 2.3 and 2.4, they show how the original measure, the one for all the particles, MNTE, can be written as an average over this field. For a fixed fiedler, the particles become independent, and fiedler itself is distributed according to this renormalized measure, nerf T fiedler. This decomposition is key.
It lets them connect the properties of the full system to the properties of just one particle and the distribution of failures. And section 2.2 uses this to connect the LSI for the full system to the LSI for that renormalized measure. Proposition 2.1 is the main result here.
It says if both the renormalized measure and the single particle measure, with an extra field term, satisfy an LSI, then the full measure does too. And the constants are related in a specific way.
Right. They use a technique called entropy decomposition to prove this. It's a common trick in this field. You basically split the entropy of the full system into the entropy of the conditional measure for fixed error and the entropy of Dalois itself. And they use a covariance inequality, lemma 8.1, to help bound some of the terms.
Okay, lots of technical details, but the main idea is that if more NERT satisfies the LSI, then we're good. So how do they show that?
Section 2.3 is all about that. Lemma 2.2 connects VT phi back to the coarse grain's free energy. It gives a formula for VT phi in terms of handles and tiles, and the distance between file and time. And it says the points that minimize these two things, they're the same. The proof uses large deviation theory, specifically Sanoff's theorem. It's a way to connect the behavior of a large number of particles to the probabilities of different macroscopic states.
Right, so the free energy and this renormalized potential, they're deeply connected. And Proposition 2.3 uses this connection. It says that if time satisfies the PL inequality, then NERT satisfies the LSI.
Exactly. The PL inequality for sign, it implies a certain kind of convexity for V-tilers. And for these kinds of measures, if the potential is convex enough, then you get the LSI. So we've gone full circle. PL inequality for the free energy implies LSI for the renormalized measure, which all right, let's dive right in. Today, we're going deep, really deep into the world of mean field particle systems.
Oh, yeah, tons of particles all interacting, but weakly, each with every other. Fascinating stuff.
It is. We're talking huge numbers, so understanding how these systems reach equilibrium, well, it's not exactly straightforward.
Right, right. And that's where a really key tool comes in, the Log-Sobolev inequality.
The Log-Sobolev inequality. It sounds kind of intimidating, to be honest. What does it actually tell us about these systems?
Basically, it gives us a way to measure how fast a system forgets its initial state, how quickly it settles down into equilibrium.
So it's about the speed of that forgetting, the speed of relaxation.
Exactly. And we're going to be unpacking a really important paper on this.
Oh, which one?
It's called A Criterion on the Free Energy for Log-Sobolev Inequalities in Mean Field Particle Systems by Bauerschmidt, Bodineau, and Dagallier. A mouthful, I know.
Just from the title, it sounds like they're linking this forgetting process to the system's energy. Is that right?
You got it. They basically give us a condition based on the free energy that guarantees the Log-Sobolev inequality holds. And importantly, it holds uniformly no matter how many particles we have.
Uniformly.
Yeah.
So the size of the system doesn't mess things up.
Nope. And you know our listeners, they love the math, so we're going to get into the nitty-gritty, right? Equations, proofs, the whole works.
Fantastic. I'm ready to get my hands dirty. Where should we start?
Well, with the free energy, obviously, it's a macroscopic quantity, right? It tells us about the overall state of the system.
Okay, big picture stuff.
Right. But we're going to connect that to the microscopic details, to how individual particles behave as they relax toward equilibrium.
The individual versus the collective. Classic theme. So how does the Log-Sobolev constant, that measure of forgetting speed, get influenced by this free energy?
That's the million-dollar question. And we can't forget about temperature, right? And those all-important interactions between particles.
A lot to untangle.
Yeah.
So how do Bauerschmidt and his colleagues set the stage in their paper?
Right off the bat, they give us equation 1.1, which describes the Langevin mean field dynamics. It tells us how the position of each particle, let's call it she at time t, so she of t, changes over time.
Equation 1.1. Okay.
Yeah.
I'm taking notes. So what are the forces at play here driving these changes in position?
Three main players. First, we have the gradient of the potential, she, g of t. You can think of V as this external potential energy landscape.
Like a topographical map with hills and valleys.
Yeah, exactly. Particles will want to move downhill towards regions of lower potential energy. This is often a confinement potential, keeping the particles from just flying off to infinity.
Right, like gravity holding us down to Earth. What's the second force then?
That's where the mean field part comes in. It's a sum over all the other particles, all the J's, not equal to our I, of course, of the gradient of the interaction potential W, evaluated at the positions of the particles.
Okay, so each particle feels the influence of all the others through this interaction potential W.
Precisely. But there's a crucial factor of 1nt in front, scaling it down by the total number of particles n and the temperature T. So each interaction is weak, but it's with everyone else.
Weak ties, huge network. I'm starting to see the picture. And the third component.
That's the random part. Check 2 d by of t. That's the Brownian motion term, the jiggling around due to thermal noise at temperature T.
So some inherent randomness, like a cosmic dice roll.
Yeah, think of it as constant jostling from the surrounding heat bath.
All right, so the movement of each particle is a combination of external potential, average interactions, and random jiggling. It's a delicate dance.
It is. They also point out the connection to the McKeon-Vlasov equation. This describes the evolution of the probability distribution of a single typical particle.
So instead of tracking each particle, we look at the overall probability of finding a particle in a certain place.
Precisely. But they're very clear that they're focusing on finite n, not the infinite limit.
Finite, but potentially massive. What comes next?
The invariant measure, MNT. Think of it as the equilibrium probability distribution of the whole system.
The state it settles into after ages and ages, if it's well behaved.
Right. And as you can see from equation 1.2, it depends on V, W, T, and of course, N.
Okay, so all our players are involved.
They even define this AV in equation 1.3, which would be the equilibrium for a single particle if there were no interactions. It's sort of the baseline.
Right, the lonely particles scenario.
And they point out that for MNT to make sense, the partition function ZNT in equation 1.4 must be finite. Otherwise, we can't normalize it.
Right, it needs to be a proper probability distribution adding up to 1.
Now comes the free energy functional, FTA, in equation 1.5. It tells us about the energy landscape of the system.
Ah, free energy, that concept from thermodynamics. What does it look like here?
It's got 3 parts. First, the entropy term, which measures disorder.
More disorder, higher entropy.
Yep. Then the potential energy term, reflecting the influence of V.
The landscape we talked about earlier.
And finally, the interaction energy, which depends on W and T.
All the pieces coming together.
And they note that it's only well-defined if Ra has a density function.
Okay, so it can't be too wild. What about finding the best state? The one that minimizes this free energy?
That's where things get interesting. Generally, at least one minimizer exists. They cite some general results for that, but whether it's unique depends on the temperature.
Oh, so temperature is key.
Yeah, at high enough temperatures, you typically have a single unique minimizer.
One stable equilibrium.
But at lower temperatures, you can have multiple minimizers, maybe even infinitely many.
That sounds like a recipe for phase transitions.
Exactly, different stable states competing. And that brings us to the critical temperature, TD.
The point where things start to shift.
Yep. Equation 1.6 defines Tc as the lowest temperature above which you always have a unique minimizer for Ft. Above Tc, one stable state. Below, potentially many.
Okay, so PC is the dividing line. Now, how does this all relate back to the Log-Sobolev inequality?
Well, they say that MNT satisfies a Log-Sobolev inequality if equation 1.7 holds for all suitable functions f.
Let me see, equation 1.7. It's got an entropy term and a gradient term. What does it actually mean for this system?
Think of it this way. The left-hand side measures how far the distribution of f is from the equilibrium distribution, MNT.
Okay, measure of non-equilibriumness.
And the right-hand side is related to how much f changes across different configurations.
So how smooth or weakly it is.
Exactly. The inequality is saying you can control this distance from equilibrium using information about how much f changes. The constant awe in the inequality, the Log-Sobolev constant, tells you how strong this control is.
So larger go means a tighter bound, and that should correspond to faster relaxation to equilibrium.
Precisely. And their big goal is to find estimates for this awe, this NLST, that are uniform in n, so they hold no matter how many particles we have.
Because we want to understand what happens as the system gets really large.
Right. They don't want the relaxation to become arbitrarily slow just because we have tons of particles. And they're aiming to connect these uniform bounds back to the free energy.
Ah, back to that central player.
Hmm.
And what does the existing research tell us about these uniform bounds?
It's a mixed bag. If the interaction part of the free energy is non-convex, things can get tricky.
Non-convex, meaning it has multiple dips and bumps.
Right, and that can lead to phase transitions. In those cases, or NST usually vanishes as n gets large.
The system gets stuck in those dips, those metastable states, and relaxation slows down.
Exactly. Gentile showed that this happens quite generally.
But there's good news too, right?
Yeah. For high temperatures or weak interactions, things are usually much nicer.
No phase transitions to get in the way.
Right, and you can get those uniform bounds on NLST. Malyu's work shows that. And more recently, people have been looking at flat convex interactions.
Flat convex, that sounds specific.
It is, but it guarantees no phase transitions, and you get uniform Log-Sobolev inequalities.
Okay, so the nature of those interactions is crucial. How do Bauerschmidt, Bodineau, and Dagallier tackle this whole problem?
They build on some really clever renormalization techniques, originally by Benarus, Guianet, and Zaitouni.
Renormalization, I remember hearing about that in physics. It's about looking at the system at different scales, right?
Yeah, basically. Here, it helps us simplify the problem by focusing on the average behavior rather than the individual details. And it works well for general interactions, even random ones.
Robust, I like that. The introduction then mentions quadratic interactions specifically. What's so special about them?
They're the simplest non-trivial case. Think of wxy oppo x equal qy. That's quadratic. And they serve as a great starting point to get a feel for the math.
Okay, a stepping stone.
And they can push the analysis all the way to TC for these quadratic interactions, even on random graphs. They use spectral decomposition, which helps reduce the problem to looking at a single dominant mode.
One mode ruling them all.
Pretty much. And they note that similar techniques have worked well for discrete models, too.
So it's a versatile approach. But what about more complex interactions, those that aren't quadratic?
For those, they focus on fully connected graphs' standard mean field. They already know the story for flat convex interactions, so they're after those non-convex cases where phase transitions lurk.
Where things get really wild.
And their solution, they generalize this mode decomposition idea. Instead of just one dominant mode, we have a bunch of important ones.
So the complexity gets reflected in the number of modes.
Right. And they contrast this with their work on short-range interactions, where scale decomposition was the key. Mean field systems are all about the mean field, a single scale.
Okay, the nature of the interaction dictates the tools I'm following. And they make an assumption to simplify things, assumption 1.1.
Right. They assume the confinement potential V can be split into a nicely behaved part, VC, and a leftover part, EE, that's either Lipschitz or bounded.
Keeping things tidy. All right, that was a really thorough walkthrough of the introduction. I'm starting to feel like I can actually understand this stuff. Where do we go from here?
Now, they get into the details, starting with those quadratic interactions. Section 2 is all about proving theorem 1.3 and corollary 1.4. They're going to show us how they do it, one step at a time.
I'm ready. And they start by introducing this renormalized potential.
Yep, a really key idea. It's defined in equation 2.5 and will make things much easier to handle.
Easier? How so?
It lets us shift our perspective, look at the system in a different light, and it'll become clear why they call it renormalized as we go along.
Okay, I'm intrigued. They also mention this GHS class of double well potentials. I remember that from the intro.
Right. They'll show that for those potentials, the temperature where this renormalized potential becomes nicely convex is exactly TC, that critical temperature.
Yeah.
And they'll also tell us how the Log-Sobolev constant behaves near TC.
A lot of juicy details to uncover. So how does this renormalized potential actually come about?
They start with this neat identity equation, 2.1. It shows you can rewrite the exponential of the interaction term that sum over pairs in terms of an integral over an auxiliary field.
An auxiliary field. So another layer's abstraction.
Sort of, but it helps us decouple the particles. Instead of interacting directly, they interact through this field.
Indirectly through an intermediary.
And that makes calculations easier. They use this identity to decompose the expectation of any function f under the original measure m and t.
Splitting it up into smaller, more manageable chunks.
Exactly. This leads to equation 2.3, where we have this new measure, ET, on the space of, and another measure, ET, conditioned on a fixed value of.
Okay, so ET tells us about the distribution of this field, and ET describes the particles given a specific.
You got it. And ET is a product measure, meaning the particles are independent given. It's like each particle sees this common external field.
I see, a shared experience. What about ET? What governs its behavior?
That's where the renormalized potential VT comes in. ET is proportional to ENVT. VT basically captures the effective potential energy of the field, and it's defined in equation 2.5.
Okay, so VT is all about, and it depends on the original single particle potential V. So the single particle properties influence the behavior of this collective field.
Exactly. It's a beautiful connection. And they point out that the normalization constants nicely cancel out, so we're dealing with proper probabilities.
Good. No mathematical shenanigans. They then claim that if this ET satisfies a Log-Sobolev inequality with a certain constant, then the original measure MNT does too.
That's proposition 2.1. And the constant they need for ET is proportional to n?
Proportional to n, that seems important.
It is. It ensures that when you go back to the original measure, you get a Log-Sobolev constant independent of n.
Ah, that uniformity we're after.
And they mention that if VT is sufficiently convex, then ET automatically satisfies the required Log-Sobolev inequality thanks to the Bakry-Emery criterion. They'll connect this to the coarse-grained free energy later.
The plot thickens.
First, they prove proposition 2.1. They use the fact that both ET and HOT satisfy Log-Sobolev inequalities and then decompose the entropy using equation 2.7.
Entropy decomposition, breaking it down into manageable pieces again.
Right. And then they have to analyze the gradient of this function g, which is the square root of the conditional expectation of FA.
Gradients.
Yeah.
Always so much fun.
Well, it leads to equation 2.9, where they have to deal with a covariance term.
Covariance, that measures how two things vary together.
Yep. And they handle that using a technical lemma from the appendix, lemma A.1. It lets them relate the gradient with respect to gradients with respect to the particle positions.
Always good to have a lemma up your sleeve.
And by putting all these pieces together, they prove proposition 2.1, which gives us the bound on the Log-Sobolev constant for MNT.
A key step.
Now, the connection to the coarse-grained free energy, that's section 2.3, they want to show that if this coarse-grained free energy, Ft, satisfies a Polyakov-Rasevitz inequality, then Ht has the Log-Sobolev property we need.
So a macroscopic property implying a microscopic one.
Exactly. That's proposition 2.3. But first, they introduce lemma 2.2, which relates the renormalized potential Vt to Ft. It gives us those variational formulas in equation 2.11.
Variational formulas, always a good sign.
They show that Vt can be written as an infimum over probability measures involving the full free energy Ft, or as an infimum over the mean M involving the coarse-grained free energy Ft.
Two ways of looking at the same thing.
Exactly. And they prove this using Sanoff's theorem, that powerful tool from large deviations theory. They even point out the connection to the Hopflax formula, but that's a bit of a side note.
We'll let that one slide.
The important takeaway, Vt and Ft have the same number of global minimizers. They're deeply connected.
Okay, so their fates are intertwined.
Now, back to proving proposition 2.3, the key. If a function satisfies a PL inequality, then a measure with density proportional to e to the minus n times that function satisfies a Log-Sobolev inequality with a constant proportional to n.
Like those earlier results they cited.
Precisely. So they just need to show that if Ft satisfies PL, then Vt does too.
A domino effect.
Right. They use the variational formula for Vt, assume Ft is sufficiently smooth, and then carefully analyze the gradient of Vt.
And through a series of well-placed inequalities.
Boom. Vt also satisfies PL. And that wraps up the proof of proposition 2.3.
Which means theorem 1.3 is also proven. The chain of implications is complete. I'm impressed.
It's quite elegant, right? Now, let's look at those double well potentials. Remember corollary 1.4, which talked about the Log-Sobolev constant vanishing near Tc?
Vaguely. Remind me.
It basically said that for those special potentials, the Log-Sobolev constant goes to 0 linearly as we approach Tc from above.
Okay, things slow down near the phase transition. Makes sense.
Section 2.4 is dedicated to proving that, and the key is showing that Vt is uniformly convex for temperatures above Tc.
It's reform convexity. Good for Log-Sobolev, right?
You bet. They first introduce assumption 2.4, which defines the GHS class potentials. They have some specific properties, and our favorite double well potential, Vx x equals all by 2, belongs to this club.
Exclusive club membership.
And being in this club comes with perks. Equation 2.20 gives us a bound on the variance of the tilted single particle measure.
A useful tool for their arsenal.
Then comes proposition 2.5. It tells us two things. First, that Tc is equal to the variance of x under the original single particle measure.
TC linked to the variance. That's cool.
It is. And second, it gives us a formula for the infimum of the second derivative of Vt.
The second derivative, the one that tells us about convexity.
Exactly. And it turns out this infimum is positive if and only if T is greater than Tce.
Meaning Vt is uniformly convex above Tce. The stars are aligning.
Right. Then they prove a lower bound on the Log-Sobolev constant in proposition 2.6. It's proportional to Ttc, so it vanishes linearly at Tc as we expected.
Halfway there.
Now for the upper bound, proposition 2.7. This one uses the Poincaré inequality, which is a consequence of the Log-Sobolev inequality.
Okay, a weaker inequality, but still useful.
They choose a clever test function. The average particle position scaled by 1 or n. This gives them an inequality involving the susceptibility.
Susceptibility, measuring how much the system responds to a nudge.
Yep. They use the measure decomposition again, expand things around 0, and use the convexity of Vt to get concentration near the mean of.
Lots of clever tricks.
Then they bring in the places method to do some asymptotic analysis as n gets large. And that gives them the upper bound on the Log-Sobolev constant, also proportional to Ptc.
So upper and lower bounds matching, both vanishing linearly at Tc. Case closed.
Nicely done. They also mention you could use similar methods to analyze the behavior at Tc itself, but they leave that as an exercise.
An exercise for the dedicated reader.
Onward to section 3, where things get even more complex. Quadratic interactions on random graphs.
Random graphs, so not everyone is connected to everyone else anymore. Sounds messy.
It is, but they manage it. They start by introducing assumption 3.1, a condition on the adjacency matrix of the graph.
The adjacency matrix, that tells us who's connected to whom.
Right. They need this assumption to ensure the graph has a good spectral gap, a large separation between the biggest eigenvalue and the rest.
Spectral gap. Sounds like something from linear algebra.
It is, and it's a key property of expander graphs, which are well connected even if they're not dense.
Ah, so even with sparse connections, we still have good mixing.
Exactly. Lemma 3.2 then shows that both random regular graphs and Erdős-Rényi graphs, under suitable conditions, satisfy this spectral gap assumption with high probability.
So they're focusing on a realistic class of graphs.
And remark 3.3 points out that the specific form of the projector P isn't crucial. It's all about that spectral gap.
Okay, the essence is what matters.
Then comes the measure decomposition, section 3.2. They introduce a reduced adjacency matrix B, which captures the deviations from the average connectivity.
The quirks of the graph.
And they use B to decompose the measure, much like they did in the fully connected case. We get those new measures, HBRT and BRT, in equations 3.11 and 3.9.
So MEDRT describes the field again, and BIT is the conditional measure for the particles.
Right. But now WDRT is not a simple product measure anymore. There are those residual interactions due to B.
The graph structure leaving its mark.
They also define those measures, 0T and new RT, which are the corresponding measures for the fully connected case. They're going to use those for comparison.
Okay, a benchmark to measure against. And theorem 3.4 is the main result for these random graphs.
It says that if the graph satisfies assumption 3.1, if the potential is in the GHS class, and if the temperature is above TSE, then the graph-based measure satisfies a Log-Sobolev inequality.
Ah, similar to the fully connected case.
Exactly. The constant in equation, 3.15, looks a lot like the one we had before, with an extra term that goes to 0 as n gets large.
So for big graphs, the behavior is almost like the fully connected system.
And they point out that this proves part A of theorem 1.5, the one about the high temperature behavior on random graphs. The low temperature part comes later.
Okay, one step at a time.
The proof of theorem 3.4 uses the entropy decomposition again, equation 3.16, but now adapted to the graph-based measures. They need two supporting propositions
To handle those new measures with B in them.
Exactly. Proposition 3.5 says that the fluctuation measure BT satisfies a Log-Sobolev inequality. And Proposition 3.6 says that if the mean field renormalized potential V0T is uniformly convex, then the graph-based one, VBT, is also uniformly convex for large N.
Convexity is key.
Right. Then they prove theorem 3.4 using these two propositions. They bound the first term in the entropy decomposition using Proposition 3.5, then use Proposition 3.6 and back reemery for the second term.
Back to our trusty tools.
Yep. And lemma 8.1 comes in handy again. They put it all together and arrive at the Log-Sobolev constant in equation 3.24.
A satisfying conclusion.
Now for those propositions. Proposition 3.5 about BT is proven in section 3.4. They introduce this shifted matrix C and potential U and then rewrite the measure using moment-generating functions for Gaussian vectors.
Gaussian magic.
It is, right. This gives them a decomposition of CHT, which is a generalization of BT. Then they show that this decomposed measure satisfies a Log-Sobolev inequality using the entropy decomposition again and applying the known results for product measures and for measures with convex potentials.
Divide and conquer, a classic strategy.
And section 3.5 is all about proposition 3.6, comparing those renormalized potentials.
Showing that VBT inherits the nice convexity from V0T.
Precisely. They use the measure decomposition, carefully estimate the variance of x1 under BT, and then put it all together to show that the second derivative of VBT is nicely bounded.
Lots of careful calculations.
It's a bit technical, but it pays off. And finally, we have section 3.6, where they tackle the low temperature case for random graphs, proving the second part of theorem 1.5.
Ah, the part that says the Log-Sobolev constant vanishes below TC.
Yep. They show that the Poincare constant for the graph-based measure is exponentially small in n when t is less than tc. And since the Poincare constant is an upper bound on the Log-Sobolev constant, that means the Log-Sobolev constant must also vanish as n gets large.
Okay, so they're using the Poincare inequality as a tool to get at the Log-Sobolev constant.
Right. They prove this by constructing a special test function, FR, which captures the bimodality of the equilibrium distribution below TC.
Bimodality meaning the distribution has two peaks.
Yep. Yep, one around each of the two stable states that emerge below TC.
Makes sense.
They use this test function to estimate the spectral gap for the fully connected measure first, and then they show that the same test function works for the graph-based measure, provided the graph has that good spectral gap from assumption 3.1.
So they leverage what they learned about the fully connected case to understand the graph-based case.
Exactly, it's a clever strategy. And with that, they've covered quadratic interactions on both fully connected graphs and random graphs above and below TC.
Ooh, that was a lot.
It was. Now, on to the main event. General interactions, no longer restricted to the quadratic case. That's section 4.
Where they'll unleash the full power of their mode decomposition method.
You bet. They're going to prove theorem 1.8, that big result that links the Log-Sobolev inequality to the strong convexity of the coarse-grained free energy in the space of modes.
Sounds intimidating.
It is a bit, but they break it down nicely. They first generalize the renormalized potential to this multi-mode setting.
More modes, more complexity.
Right, but the idea is the same. They define this multi-mode renormalized potential, VT, in definition 4.1. It's a bit more abstract now, living in a Hilbert space.
Hilbert space. That's a fancy way of saying a vector space with some extra structure.
Exactly. It's a space where you can measure angles and distances, which is important for their analysis. They define VT in equation 4.7, and it again involves the coarse-grained free energy FT, but now in this multi-mode setting.
So they're building on what they did before, extending it to a more general framework.
And then they state theorem 4.2, which is the multi-mode version of what we saw for quadratic interactions. It says that if this VT is strongly convex, then the original measure satisfies a uniform Log-Sobolev inequality.
Strong convexity again, the hero of the story.
It seems so. And then lemma 4.3 connects this to the coarse-grained free energy. It says that FT is strongly convex if and only if VT is strongly convex. They'll prove this later.
A nice equivalence to have. Makes things simpler.
Right, and they point out in remark 4.4 that it's enough to prove theorem 4.2 for a finite number of modes. That'll make things easier to handle.
A welcome simplification.
Yeah.
Now, the proof of theorem 4.2. It's a long one, split into several parts.
They start by decomposing the measure again, this time using Gaussian measures on the Hilbert space. It's similar to what they did before, but more abstract.
More abstract, more powerful.
Hopefully. This leads to equation 4.12, where they have a new fluctuation measure now that depends on this generalized field.
Their multi-mode field.
Yep. And they define the non-quadratic part of the renormalized potential UNT and its limit UT as n goes to infinity.
Okay, so they're still thinking about what happens as the system gets large.
Always. Then they analyze the fluctuation measure in section 4.2.2. Proposition 4.5 gives us bounds on its Log-Sobolev constant.
Those bounds are essential for controlling the fluctuations.
They have two kinds of bounds, one for large n and another one that holds for any n. Both involve the norms of those components of Feg and the interaction potentials.
So they're carefully tracking how everything depends on the details of the interactions in the field.
Then in section 4.2.3, they look at the renormalized measure. Proposition 4.6 says that if VT is strongly convex, then a certain integral involving gradients is nicely bounded.
Gradients again, always popping up.
Can't escape them. This proposition relies on proposition 4.7, which bounds the difference between UNT and UT.
Showing that UT is a good approximation for large n.
Right. And then lemma 4.8 provides the key connection. If VT is strongly convex, then the renormalized measure satisfies a Log-Sobolev inequality.
All the pieces falling into place.
And finally, they combine all these results in section 4.2.4 to prove theorem 4.2. They use the entropy decomposition, those bounds from the propositions, and a Gaussian identity from lemma 4.9. It's a bit of a tour de force, but they show that the original measure MNT satisfies a uniform Log-Sobolev inequality.
Fantastic.
Upside.
So they've tamed those general interactions. What's left?
Just the proof of lemma 4.3, the one that connected the strong convexity of FT to the strong convexity of VT at section 4.3.
Ah, the missing link.
They prove it by first assuming FT is strongly convex and showing that this implies VT is also strongly convex. Then they do the reverse, using a Legendre transform-like relationship between FT and VT.
Elegant and symmetrical.
And lastly, there's Appendix A, where they prove lemma A pot 1, that technical lemma about covariance bounds. They use Langevin dynamics, the generator of the dynamics, integration by parts, Cauchy-Schwarz, the whole shebang.
A powerful toolbox.